Thank you everyone for coming. um, if you would like to play along at home during the talk, then the slides are already online. There's a couple of links in them to further resources in case you're into that sort of thing. If my presenter remote would work. There we go. So my name's Larry Garfield, or at Krell on Twitter. If you want to make fun of me online during this talk, that's where you do so. I generally encourage it. I am, for now, the Director of Developer Experience at Platform SH. We're a continuous deployment cloud hosting company and one of the sponsors tonight. I'm also a member of the PHP Fig core committee. It's kind of like the United Nations of PHP with all the good and bad implications that has. It's kind of PHP's de facto standards body. And I'm the author of actually a couple of books now, most notably Thinking Functionally in PHP, which we'll be giving away a copy of at the end of this talk. And I actually am looking for a new position. The DevRel team is getting downsized at Platform, so I am on the market. But that's not what I'm actually here to talk about. What I'm here to talk about is this. This is a computer. It is a very old computer, specifically an IBM System 360 Model 20. This was announced back in 1964, and System 360 was the world's first complete range of compatible computers. That is, multiple models and multiple variants of the same computer design that were compatible with each other. You could actually run software from one System 360 variant on another variant, which meant for the first time in computing history, you needed to have a distinction between the computer architecture and the implementation, because you needed to have the architecture be compatible with multiple implementations. It was developed over the course of 2 years because everything takes a long time in tech, but it shipped for over a decade. And one of the reasons why it needed to be so flexible is different models had different hardware. For example, some of the fancier versions had this crazy new thing called spinning disk storage, where you could store thousands of bits of information on a device only the size of a refrigerator. And this was cutting edge technology and way better than the reel-to-reel tapes of earlier machines. System 360 went on to be one of the most influential products in computing history, and its legacy is still with us today. For example, why is a byte 8 bits in size? It doesn't have to be. Prior to System 360, the most common byte size was 6 bits. System 360 used 8-bit. And this caused a problem, actually, with earlier computers that only had 6 bits. That's not enough to include all uppercase and lowercase letters and numbers and necessary punctuation. So they could only include uppercase or lowercase numbers on those computers. And the team that was working on developing this did the research and found that all lowercase is easier to read than all uppercase. So they went to their boss and presented this information, and their boss said, but we're IBM. We can't have our name in lowercase. And so all uppercase became the default for the next 30 years, even though it is in fact worse. But 8-bit bytes, so you can thank System 360 for that. It also introduced the idea of byte-addressable memory. Prior to System 360, you could write programs that accessed individual bit offsets in memory. System 360 introduced the idea of accessing memory at the byte level and reading it byte at a time instead of bit at a time. It also introduced EBCDIC, which was a character encoding system that nobody uses anymore because ASCII took over and conquered the world instead. So, not everything from System 360 lives on. However, System 360 itself lives on in the IBM Z-Series mainframe, which you can still buy today and is in fact backward compatible for many programs written for System 360. 40-year-old, 50-year-old software still works on this computer, which is damn. Also, it runs PHP, so there's that. The lead team for System 360 was these two people. Gene Amdahl was the lead architect, and Fred Brooks was the lead manager, project manager for it. Brooks is actually the person who coined the term computer architecture. After the project was over, they drifted apart, went their separate ways. The team broke up, like they do, and a lot of the leads ended up in academia, like you do. And 10 years later, Brooks wrote a book called The Mythical Man-Month, which was a collection of essays talking about System 360 and its development and the research that had been done since on how to manage huge software projects, because they had to build all the software for System 360 from scratch. And an anniversary edition came out in 95 that included a look back at his predictions and his statements and his recommendations from 20 years earlier, and included some additional information as well to say, all right, this is what I said. Was I right? Are my recommendations still accurate 20 years later? And his conclusion, which is pretty accurate, was, yeah, kinda. Nothing really changed in 20 years because technology changes. Humans don't. Managing software projects is about humans, not technology. So most of those recommendations are the same. So it's been another 20 and some odd years. What I would like to do is go back and say, all right, nearly 50 years later, is it still valid? Now, I'm going to follow a different outline from Brooks here, but summarizing the ideas he talks about. One thing that he does do that is not stood the test of time is way overuse of male pronouns. But put that aside, there's absolutely nothing gendered in any of what we're talking about here at all. I'm also going to pick on a couple of open source projects as examples, but I could pick on any of them. These are just the ones I'm going to pick on for this audience. So you may have heard of the phrase Brooks Law. Adding people to a late software project makes it later. Why is that? This line comes from this book. Why is that? Because communication is hard. Communication is very hard. Why is communication so hard? Well, part of it is that it gets worse exponentially. If you have two people collaborating, you have one line of communication between them. If you have three people communicating, you have three lines of communication. Four people communicating and collaborating means 6 lines of communication, and so on and so on. The number of lines of communication you need goes up combinatorically rather than linearly. Don't worry about the math. The takeaway here is every time you add people to a team, you add communication overhead, and the amount of overhead you add goes up faster than the number of people in the team. Why is that? Mostly because tasks are not parallelizable. Most development tasks cannot, in fact, be completely parallelized. This is a management talk, so there have to be Dilbert comics in it. I hired all of you because the project will take 300 man days to complete. There are 300 of you, so I want you finished by 5 o'clock, clean out your desks, you're all fired. Clearly, this is ridiculous. But it is the way that some not good managers think about development. And this is true for skilled tasks and even for unskilled tasks. Why? As an example, a couple of years ago, I helped friends of mine move from Chicago to New York. So they ordered pizza and had all of their friends come and help pack up their apartment. And they had something like 50 or 100 boxes. So all they need is 100 friends and we'd be done in seconds. Of course not. The apartment only holds so many people at a time. We only had 2 dollies. We had 1 truck. There was 1 elevator. The people packing the boxes need to know what is in them. And so they have to coordinate what's going to be in them. The people packing the truck need to keep track of which boxes are on top of which. So they need to be the same people who are going to be there at the other end in New York to unpack. The same problem happens in technology. You need to develop, you need to build out the database before you can build the code that's talking to the database. You need to do the design for the front end before you can implement the front end. These tasks block each other way more than you think. Now, of course, one thing we never did figure out is why anyone would want to move from Chicago to New York, but eh, that's another matter. Fundamentally, though, people and months are interchangeable commodities only when a task can be partitioned among workers with no communication among them. If you actually have people needing to talk to each other, then throwing people at a problem won't actually help. In fact, it can be counterproductive. More Dilbert, of course. How long will your project take if I add 2 people? Well, 1 month for training, 1 month for the extra complexity, and 1 month to deal with their drama. It takes more time to add people to the team because someone on the team has to stop working and bring those people up to speed. And those people will have ideas that may not fit with how the project is running that you need to work through and get them the right campfire knowledge about the project. There are some exceptions to this. If you're really early in the project, then the cost of adding people is lower because there's less to teach them about and longer to amortize that cost over. It also depends on the number of swim lanes. Swim lanes is a concept from Agile. Basically, it's the number of parallel tasks on a project you can have people working on without bumping into each other, without getting git merge conflicts between everything they're doing, essentially. And different projects will have a different natural number of swim lanes. Sometimes it's one. Some projects, putting more than one person on is actually counterproductive. Could be 2 or 3. It's rarely more than a half dozen in my experience. The number of, I would usually argue that the max number of developers you want on a team is the number of swim lanes plus 1. That plus 1 is to allow for people doing code review, someone to go on vacation, someone to get sick. More than that, and you're going to have people bumping into each other and they're going to spend more time fighting over git merge conflicts than you're going to save by having more people on it. Note this number of developers. This does not include designers or project managers. It means people writing code and interacting with Git. This applies to technology too. This is Amdahl's law, the same Gene Amdahl we talked about. Again, don't worry about the math. That's not relevant. The important point here to see is Amdahl's law gives, quote, the theoretical speedup in latency of the execution of a task at fixed workload that can be expected of a system whose resources are improved. In other words, this is a measure of how much CPU you can just throw at a problem to make it faster. And the more parallel it is, the more resources you can just throw at a problem and it goes faster. But even at 95% parallelism, which is extremely rare, there's still a point of diminishing returns. If your task is 90% parallelizable, then throwing more than 256 CPUs at it is not worth the effort. With barely parallelizable tasks, throwing more than 3 or 4 people at a problem is not going to help. So that's his argument anyway. What do you think? Is that true? Yep, I'm going to say yes. This totally matches my experience. In fact, when I was first putting this talk together a few years ago, I just whined on Twitter that the problem with writing a talk based on the Mythical Man-Month is there's at least 2 talks worth of content, all of it good. And someone helpfully pointed out that I should just get a second speaker on stage and give both halves of the talk simultaneously. That way we can fit in twice as much material. Because of course that's going to work. But when you think about it though, a lot of the major open source projects have an awful lot of people working on them. Any Laravel developers in the room? 548 contributors as of today. That's an awful lot of communication channels. What should we learn from this? Something Brooks also talks about is why estimates are always wrong. I don't care who you are, odds are your estimation skills are nowhere near as good as you would like to think they are. And if you think they're terrible, they're probably worse. Why? Brooks points out that what you're estimating is not the full product. When you estimate, you're a developer, what you're estimating is the skunkworks project. You're estimating the throw it together in your garage level of completeness. But building that out to flesh it out with tests, good error handling, performance optimization, all of the other stuff that makes it a true product takes 3 times as much work as that initial proof of concept. It is 3 times as much work to complete a project as to just build out the happy path. And if you want something that people can build on, then you need to standardize your interfaces. You need to uh, do integration level testing. There's 3 times as much work for making something that's a true robust platform. Together, that means your final product, what you actually need at the end, is 9 times as much work as what you think you're estimating. You think you're estimating, can I make my first test pass? What you're actually building is 9 times as much work as that. Notice I said tests there. One of the things Brooks points out is that a substantial bank of test cases exploring the input range and probing its boundaries must be prepared, run, and recorded if you want to have anything approaching a programming system product, this complete, real version of what you want. What does that mean? It means automated testing was already understood as a thing in 1975. What's your excuse? You don't have one. No, this does not mean that writing tests takes 3 times as long. It means fixing all of the bugs that writing tests finds is going to take you 3 times as long, and you need to budget for that. Related, how fast can you code? Just think for a moment. How fast can you produce code? Whatever you just thought of is wrong, because I didn't tell you enough information. Extrapolation of time for the 100-yard dash shows that a man can run a mile in under 3 minutes. The current best is 3 minutes 43 seconds. Because when you're running a mile, you're going to run slower than when you're running a 100-yard dash. And this is in fact true for technology too. In fact, studies found that the amount of effort it takes to add code to a code base goes up exponentially with the existing size of the code base. So the more code you have, the more work it takes to add code to it. Why? And this is true even without communication, even if there's one developer on the project. Why is that? 2 main reasons. One, there's more interaction points internally in the code. So your odds of a change here, breaking something over here, goes up the more over here's there are. And also just the limits of human memory. Your ability to hold a problem in your head is limited. There's only so much code that you can store in your own working memory. And as the code base grows beyond that, the amount of time you spend relearning what you wrote last week in a different part of the code base also goes up. Another study that Brooks quotes found that when you have a little bit of interaction within a code base, then you can add up to 10,000 instructions per year. At the other end, if there's a lot of interactions, both people and code interactions, it goes down by nearly an order of magnitude. You can add maybe 1,500 instructions per year. This is the amount of code you're going to write. Goes down the bigger your code base and the more people you're talking to in the process. Now, by large systems, this test said 25 programmers and 30,000 instructions. Remember those numbers. Of course, we said instructions here. This study was actually conducted on assembly and how fast you could write assembly code. However, follow-up studies found the exact same curve for code written in PL1, which was kind of the standard programming language before C in the late 60s, early 70s. And it followed the exact same curve, but for statements. So what can we take away from that? 2 things. One, if you have a more expressive language that gives you more power and more expressivity per statement, per line of code, you will be more productive. The language does matter to productivity. But that curve still happens. Bigger code base means you will go slower. And that is true no matter what language you're writing in. What do you think? Is he right on that one? I'm going to say yes. This is definitely my experience working on some very large code bases. But remember that number I said to remember. 25 programmers and 30,000 instructions is what we mean by large. Any Symfony devs around? 2,300 contributors to Symfony. And how many lines of code does Symfony have? Anyone want to guess? When is it going to stop? Over 500,000 lines of code. This is a very large project. And that's not even counting dependencies. That's just its own SRC directory. What can we learn from this? Brooks also talks about planning and documentation, which, according to Brooks, are the same thing. Planning and documentation go hand in hand. And in fact, you should write your documentation first before you actually write code. Why? Because only when one writes do the gaps appear and the inconsistencies protrude. The act of writing turns out to require hundreds of mini decisions, and it is the existence of these that distinguish clear, exact policies from fuzzy ones. Writing down what it is you're going to do forces you to think about what you actually should do. When I was a consultant in earlier life, all the time, we would go spend a couple of days on site with a client, learn all about their system, their business, talk to users, figure out what we want to do. I'd come back to the office, sit down, start writing to summarize for them exactly what we're going to build. And I'd come up with 100 other questions of, oh, what does it do in this situation? How about this situation we didn't talk about? What about this edge case? I like to describe it as rubber ducking with your word processor. Just writing it down in Word or Google Docs or a text file, what it is you're going to do, forces you to think through all of those extra little bits you didn't think about in the first place. That's not part of that initial skunkworks upper left quadrant proof of concept. The crucial task is to get the product defined. Many, many failures concerned exactly those aspects that were never quite specified. In short, if you don't know what you're building, you cannot possibly build it well. However, the written specification is a necessary tool, but not sufficient. The formal definition of what the system does is the code. It is precise, but not always very readable. Your documentation, your outline, or out-of-band documentation, is important, but nowhere near as precise as the code. You also need to describe why you're doing something. Code describes what, your documentation and comments, which are part of documentation, describe why. And Brooks argues that to build a system effectively this way, after you've designed it, you need top-down design, which means architect the system first, describe what you're going to do, break it down into modules, top-down, and then break those modules up into pieces as well until you have a picture of what your architecture is going to be. Then you can implement each of those individual units, test each of them individually, unit test each of them individually, and allow that process to inform backup as needed. So you run into a problem here, you can inform that, use that to inform the rest of the architecture and possibly change something. He's describing divide and conquer. This is the most basic strategy in any science or any engineering problem. Look at the problem, it's too complicated, break it down into smaller problems that are not complicated, solve those, and then plug them together. Basic engineering, basic science. He also says that you should plan to throw one away, you will anyhow. Because you don't know what you don't know until you've built it the first time and done it wrong. Naturally talk about the time you know least is at the beginning of the project, the time you know most is at the end of the project. So you don't know what it is you should have done until you've already done it wrong. There's an old joke that you should never ship version 1. In fact, Microsoft takes 3 versions to get good. Windows version 1 and 2 were terrible. No one used them, and it took until Windows 3 for them to actually, ship. It's a joke about Microsoft, but it's actually true of everybody. Your first version is the least well-informed, least well-architected version. So just plan that your first version is going to get thrown out. Now, at some point here, someone is probably saying, but Larry, you're describing waterfall. Isn't that, terrible when we all know this? And we've known this for decades. In fact, the government documents talking about waterfall that people always blame were saying that waterfall was something you shouldn't do in the first place. And yet businesses still did it, even though the government told them not to. And then they blame the government for talking about it because, we can't possibly blame private business for things. Well, Brooks looked at this and said in his follow-up in the 90s, you know why? Yes, that is kind of waterfallish. Fair play. So he refined his recommendation to design top-down but implement iteratively. What does that mean? Once you have your architecture, you implement an end-to-end skeleton. This is a complete system that will do nothing but has the framework in place. And this could be 60% of the work. This could be a significant amount of effort to build your overall picture that doesn't actually do anything. In the case of a PHP web app, it's a lot of this is handled by just the framework itself. It's, hey, can you accept requests? Can you respond to requests? Can I log in? And that's done. There's your skeleton, boom. And after that, always make sure your system ships. It is in a shippable state. It may not be useful. In fact, it is probably not useful. It is not going to solve the problem you're trying to solve, but you have a system that will compile and will serve requests and will run always. And then you grow modules into place and replace stubbed out pieces with real code that will actually do something productive rather than just be a mock that you run in production. And as you go, you learn more. You can throw away individual pieces and replace them with another. You can rewrite an individual component. You can shift the architecture over here and change these modules without changing those modules. What he's describing here is refactoring. We said before, throw away the first version always. Refactoring is the art of throwing your first version away a little bit at a time. As you learn more, you redo how the code works in order to do what it wants to do better. But he does caveat, this approach necessitates top-down design for this top-down growing of the software. You're starting with that skeleton and then you fill in the muscles and bones, but you need that skeleton first for everything to fit. He also notes common sense, if not common practice, dictates that one should begin system debugging only after the pieces seem to work. In other words, unit testing. Architect top down, but you debug bottom up. Now, someone in the audience is probably thinking, but Larry, didn't you just describe Agile? And, you should grow into place. You've probably seen this diagram at some point about how, you should build an MVP and do Agile. This is wrong. This is terrible. When was the last time you managed to successfully enhance a skateboard into a car? It doesn't work like that. Cars cannot be built out of skateboards. With this approach, you are throwing it away not once, but at least twice, if not 3 times, maybe 4. This is not how software actually works. What you really need to do is this. You start with a skeleton that supports your end goal. In this case, I want a car, so I'm starting with the A-frame and wheels and a steering wheel. I'm not going to waste time building a bicycle when I know what I actually need is a car. And then you can add to it. You can add the trunk, replace the tires, add doors to it, and so on, replacing decoupled components on top of that basic framework. And that is how you build an MVP. The first version has to be at least along the same lines as the final version that you expect to have. Otherwise, you're just going to have to delete everything and start over. This also means, contrary to what Agile will tell you, you do not build the most important feature first. You always start with the foundation. If you're building a house for someone and the most important feature for them, the reason they want this house custom made, is so that they can have a fireplace in the second floor bedroom. Is the fireplace the first thing you're going to build? No. The first thing you're going to do is pour concrete for the foundation. Because if you don't get that right, there won't be a second floor in which to have a fireplace. So, yeah, Agile is not actually right any more than Waterfall is not actually right. What do you think? Is he right? This completely agrees with my experience. So I'm going to give Brooks 2.5 out of 3 so far. In the 1995's anniversary edition, Brooks included a couple of new chapters, including an essay called No Silver Bullet, based on a talk he gave in 1986, in which he lays out 2 kinds of complexity. what he calls essential complexity and accidental complexity. Essential complexity is this is hard to do because the problem space itself is hard. Think e-commerce. If you've done e-commerce work before, why is e-commerce hard? Because commerce is hard. Because tax law is hard. Because tax law varies across all 50 states and oftentimes by city. It's just a complicated problem space. Accidental complexity is my tools are bad. Accidental complexity is the framework I'm using is poorly written, or the e-commerce tool I have is buggy. I believe the hard part of building software to be the specification, design, and testing of the conceptual construct, not the labor of representing it and testing the fidelity of the representation. Remember, he was writing initially at a time, or working originally at a time, when executing a program to see if it works required picking up your stack of punch cards, carrying it down the hall, taking the elevator down to the basement, walking down to the hall to the room with the computer, handing it to your cards to an operator, going back up to your office, waiting 2 hours to come back and have your operator hand you the stack of cards and say, there was an error on card 497, have fun. And you get to take those back to your office and stare at the punch cards for a while to figure out what you did wrong. That's accidental complexity. That is the tools we have, walking down the hall to the elevator to debug things, are terrible. And it's not because the problem space itself is complicated. We have solved those. There is now no single development which by itself promises even one order of magnitude improvement in productivity, reliability, or simplicity. He's saying this in the 80s. Not that there's no room for improvement. Better languages make us more productive. Better tools make us more productive. But we're not going to be 10 times more productive because we switch languages. The low-hanging fruit of I have a real-time debugger sitting on my laptop in front of me that I can just examine the code memory with, versus I have to stare at punch cards that were brought back from the basement. That's an order of magnitude or more improvement between those two. There is no order of magnitude improvement left once you have a real-time debugger sitting in front of you. So how can we have real improvement in productivity? How can we get more productive, more efficient when we've already knocked off all the low-hanging fruit? Well, Brooks has 3 suggestions for that. One is rapid prototyping, where we grow the system organically based on user feedback. Rather than building something and hope it works, you actually talk to users and iteratively build out your system, which we already talked about, so I'm not going to go into that further. His other recommendations are buy versus build and mentoring better architects. And Brooks states the most radical possible solution for constructing software is to not construct it at all. When Brooks started work in the 60s and 70s, you would pay $20 million for a computer. Spending $50,000 to custom write all of your software was a rounding error. The accountants wouldn't even notice. Nowadays, you can get a computer powerful enough to run a Mars rover for $10. It's this big. It'll fit in the palm of your hand. The software is the expensive part now, not because software has gotten more expensive, because hardware has gotten so absurdly, comically cheap in comparison. So if you want to save money on software, which is now the cost center, the way to do that is to reuse components. Why in the world would you write a web server? There's already several free open source ones you can use. Why in the world would you write your own spreadsheet? There are several on the market you can just use. Why in the world would you write an HTTP client? There are several on the market you can just use. Now, Brooks called this COTS, commercial off-the-shelf software. But what he's really describing is open source. This is the entire point behind open source, is we only need 2 or 3 web servers. We only need 2 or 3 HTTP clients. We only need 2 or 3 spreadsheets. Let's just write these components, share them, and never have to write them again. And that spreads the cost out among everyone. If you are not using majority open source in your programming projects today, you are wasting money. You might as well just set it on fire. It would be more useful. Every project you're running today should be at least 70% open source components. If not, honestly, you're wasting money. The way to be more productive is to write less code. And the way to be more productive, therefore, is to reuse more code, more open source code that you can share both the code and the costs with others. He also says we need to grow great designers. Now, there's an interesting shift here. In the 80s and 90s, he stops using the term architect and starts using the term designer for the same role, because software construction is a creative process. Study after study show that the very best designers produce structures that are faster, smaller, simpler, cleaner, and produced with less effort. The difference between the great and the average approach an order of magnitude. Oh my God, 10x developer discrimination. No. 10x designer. The best developer is not going to produce 10 times as much code per hour as a junior. That's not how it works. But a good designer, a good architect can design a system that requires 10 times less code to be written in the first place and has 10 times fewer edge cases you have to worry about and then code for and test for. That's where the difference comes in. Software architecture is not a programming skill. Software architecture is more akin to graphic design. It's a separate skill set that needs equal recognition with management. Brooks is very clear about this. The pay scale for architects, for designers, for people leading the design of the application of the system, they need to be on equal footing with managers in terms of their pay scale, company respect, and so forth. They're not below managers. They are technical managers, just not managing people. How do we get people who are good at that? Through mentoring. Identify candidates early. They may not be the most experienced. They may not be the best developers, but if they have the eye for design, they have the eye for architecture, they have the eye for data modeling, then those are the people you want to train as architects, as designers. You need to give them an active mentor, someone who is already doing this, who can actively mentor them in that. Give them apprenticeships. Let them take classes and coursework in architecture specifically. Let them, have solo projects where they get to design a small piece of it, and architect a small piece of it rather than just slinging code. Encourage them to work with others at conferences, at open source or on open source projects, people at other companies, even your competitors. Let them work together with others and grow their skill set. These are all things that the design world does. This is a design skill. And we need to treat architecture and design with the distinct respect it deserves as a distinct skill from programming. It's great if someone is a good architect and a good programmer, but they are different skill sets, and it's fine for someone to be better at one than the other. I'll be honest, I'm personally a pretty good programmer, but I'm a much better architect than I am. I won't write the fastest code, but I can design the cleanest flow of code. And those are different skill sets, and you need both of them on your team. What do you think? Is he right? I'm going to say absolutely yes. He definitely got open source correct. As far as architects being like designers, that is absolutely my experience working on projects of all kinds of sizes. Brooks's final point is about conceptual integrity. In fact, he says the conceptual integrity of the product as perceived by the user is the most important factor in ease of use. As perceived by the user. The goal here is to have a single mental model that the user has to worry about. And if they have one mental model, they can't have mental models that clash. You want to have one set of nouns that a user has to think about. Now he notes here, ease of use doesn't mean simple. Ease of use is it's a ratio of how much functionality you get for how much complexity you have to learn. And so a system that unnecessarily has more conceptual complexity is going to be less easy to use for the same functionality. Neither of these alone define good design. Think 3D modeling tools. These are insanely complex systems that you need a college course or 3 to learn how to use effectively. Things like Lightwave, 3D Studio Max, Blender, they are way off the edge complex, but the amount of functionality you get out of them is absolutely ridiculous in a good way. At the other end, think of a text editor, Windows Notepad or Kwrite or whatever your basic text editor is, your just system text editor. It does one thing. It has extremely low complexity. It also has extremely low functionality, which means it's just as easy to use as Lightwave, because the functionality versus complexity you have to learn is about the same. But this means you need to keep your conceptual complexity as simple as possible. Simplicity and straightforwardness proceed from conceptual integrity. In fact, Brooks goes as far as to say conceptual integrity is the most important consideration in system design. It is better to have a consistent design than more features. See also the first iPhone. It did not have copy and paste. It did not have installable applications. It did not have all kinds of features that today we were like, how could you put out a smartphone without this? But the few things it did really well, and they fit together beautifully. And that's why the iPhone was a success. Conceptual integrity not only makes it easier to use, it also makes it easier to build and less subject to bugs. Because just like the end user only needs to have one mental model of how all the pieces fit together and what to do, the developer also only needs one mental model. And you don't have 2 or 3 or 4 developers with different mental models colliding with each other, and the system just ends up as a mess in the middle. If you're into domain-driven design, you've heard the term ubiquitous language. That's essentially what we're talking about here, just from a different angle. You want to have a single mental model from the basic development and the individual lines of code up through the user interface and the user, and everything in between should be built along the same mindset. How do you get that? How do you get such strong conceptual integrity? Through smart division of labor. Brooks argues that the design must therefore proceed from one mind or a very small number of agreeing resonant minds. Not groupthink, but avoiding conflict think. And there's 2 different ways that Brooks offers to accomplish this. One is a surgical team, where the builder does nothing but build, and they have a staff whose job is to keep everyone else away and let them just do that. The idea here is if you're in a surgical ward, you have a surgeon working on someone, that surgeon is laser focused on the surgery, on getting that right, and that's it. And you have someone else there to hand them tools. You have someone else there to wipe their brow. You have someone else there to keep the the family of the patient away, to not be distracting. And that person can just do everything and nothing else then produce the output. I have never actually seen this happen in practice. So we'll talk about the other suggestion, which is to split the architect from the implementer. The architect, designer, is the user's agent. It is their job to bring professional and technical knowledge to bear in the unalloyed interest of the user, not the salesman or fabricator. You want to have one or small number of people on the same page doing the design, doing the architecture, not the whole team. But Larry, that's cathedral design. Cathedral in the bar, that's tech aristocracy. Yes, it is. And cathedrals are still standing 800 years later. Wouldn't it be nice if your code lasted 800 years? Ad hoc bazaars don't last. Ad hoc bazaars are messy and complicated and confusing, and really are not friendly to someone just entering them for the first time. Cathedrals are. Upfront design with a clear, consistent picture of what is going to happen gives you a better user experience and a better developer experience. You want more proof? Until recently, Apple has lots of good designers, but the person calling the shots was Johnny Ives. What Johnny Ives said was Apple's design is what Apple's design was, period. You don't like it? Too bad. If you have a product at Google, they've got hundreds, maybe thousands of designers working there who are very good at their job. But at the end of the day, Matthias Duarte is the one calling the shots. User interface design at Google comes from Matthias Duarte. That's his name. That's Google's brand, is Matthias Duarte. If you're using any kind of Unix-based system, then there's a standard for that. It's called POSIX. And all of these Unixes work roughly the same because there's a standard. If you don't like that standard, well, too bad. Interoperability exists because you have these standards. If you're working on the web, like I'm assuming most of us are, then you're talking HTTP and you're following the HTTP spec. And if you want to do caching, you do caching the way that HTTP says to do caching. If you don't like the way HTTP does caching, well, that's too bad, because the entire rest of the world does it the way it was designed as a standard, and it will not work unless you follow along, unless you follow the architecture that was provided to you. An architect is responsible for designing the watch dial and hands, but the implementer figures out how to actually make those work with the gears and bells. Both of these are challenging. Both of these can be fun. A good architecture supports many implementations. The same architecture exists behind an analog watch and Big Ben. It's the same architecture, same design, just bigger. A good architecture supports lots of different possible implementations. The architect must always be prepared to show an implementation for a feature they describe, but not dictate the implementation. Proving that they're not asking something impossible is the architect's job. Figuring out which specific approach is best for achieving what the architect wants to do is not the architect's job. That's the implementer's job. That's the developer's job. Let them do their job. This also helps reduce communication channels because the architect can communicate to each developer rather than every developer talking to every other developer. This is divide and conquer again, just with breaking a large system down into subsystems, and each subsystem has an architect. You have an architect for all of Google, and then you have an architect for Google Sheets, and an architect for Google presentations, and an architect for Google Docs, or whatever they call their doc version. This is an ongoing cooperative effort with high levels of communication between the developer and the architect. Architect can't just drop something from on high and walk away. That does not work. But the architect is a clearinghouse of architectural changes and decisions. And they have final authority to say, you know, that might work, but we're doing it this way. We're taking this approach so that everything still hangs together correctly. Democratic architecture is called MUD. Democratic architecture does not scale. I say this as someone who's worked on some very large democratic projects. And you can see in these very large democratic projects with no one actually steering that a lot of things end up being very inconsistent and they don't fit together very well. And they can sometimes work very well, but there's a lot of warts in them. What should we learn from this? Now, here we're talking about managing large software projects, big projects. But how big is big? Well, Brooks notes, after teaching a software engineering lab more than 20 times, I came to insist that student teams as small as 4 people choose a manager and separate architect. 4. Manager, architect, and 2 developers or implementers. Either the manager or the architect can be the boss. Either of them can be at the top of the food chain. It works either way, as long as everyone is on the same page as to which one is. Teams as small as 4 need to have a clear technical leader who can make decisions and have them stick if you want to have good, consistent, cohesive architecture. What should we learn from all of this? First, software construction is a creative process. It is not an engineering discipline, it is a creative discipline. Divide and conquer is your core strategy for, well, almost everything. But you have to do it right. And you want to do that in a way that lets you build shareable programming system products. Build loosely coupled, decoupled components that you can release as open source or replace with an open source component that you don't have to write in the first place. Which means you want your libraries to be decoupled from your framework as much as possible and put everything together using top-down design. Figure out what your system looks like. Don't just throw code at it until it works. Figure out what your moving parts are, and then start building those moving parts to plug together. And to accomplish that, you need to empower architects to make decisions. They have to be able to lead, to analyze the problem, take input from the team, and make a decision that will stick and the team follows it. Otherwise, you end up with a big ball of mud. And this is what Brooks was saying in the 60s, in the 70s, in the 90s, and it is still true today. The idea that people knew a thing or two in the 70s is strange to a lot of young programmers, unfortunately. This is from Donald Knuth, author of the book The Art of Computer Programming and considered the father of analysis of algorithms. If you aren't familiar with him, look him up. What can we learn from this? Thank you. Thank you for coming. As I said, my name is Larry Garfield from Platform SH. If you're interested in more of me, I have 2 books out now that you can get. The first, I'm going to drop a link to here in the chat, is Exploring PHP 8. It's basically a super detailed, complete, in-depth, entertaining changelog for PHP 8. All the new fun stuff in PHP 8 that you could possibly imagine. And the other is Thinking Functionally in PHP. Yes, functional programming in PHP, it's a thing, it works, you can do it, you should, and the book will tell you how and why. It also includes what has been called the most approachable and only understandable description of monads ever written. Seriously, some of the readers that have given me feedback on it was like, this book taught me monads, now I understand them. So if you've always wondered what that was about, this is the place to get the answer. And we're also going to raffle off a copy of that anytime in here, whenever the organizers say. With that, thank you very much. Happy to take questions for as long as you have them. Just go ahead and turn your microphone on and start asking, or ask in chat, either way.
I have a question.
Shoot.
So earlier, someone was talking about the entity models and relationships and how that helps you conceptualize what's going on in your system. And I was wondering if there are similar standards of conceptualizing the architecture as you're designing it. For example, it sounds like interactions are important between modules, like input-output type things.
So figuring out what your data model is a part of the architecture, which you could represent as object entities, and like Doctrine lets you build and stuff like that. That is a part of designing the architecture, but also included in that is, all right, what are your trigger events? What are your, are you going to use a command bus, or are you just going to save stuff directly? Do you want to use an ORM, or do you want to use a CQRS model, or do you want to use a event source model? Depending on what you're doing, any of those could be correct. There are even cases where, I hate to tell you, using EAV, entity attribute value, is in fact the correct architecture. Gaming, in fact, does a ton of that. When you're operating the same, you want to do the same operation against 1,000 objects at once, which may also be overlapping with other things, doing that through an ORM is terrible. Gaming works on essentially EAV for their data models, and they have to. So those kind of decisions are part of the architecture, and they are all not right, wrong, but fit, not fit, better fit, worse fit to the problem space you're solving. There are lots of tools around that. A lot of companies that will try and sell you big, complicated diagramming tools for that, but I haven't run into any that are actually worth it. Nothing can substitute truly understanding your problem space, which just takes time playing with it, experimenting with it, immersing yourself in it.
Thanks.
Sure. I can't see everyone right now, so as long as I'm showing the screen. So if you have other questions, just go ahead and speak up.
This might be more of a hypothetical question, but you brought up the PHP project. I know there's a lot of the frameworks have maybe a champion or an ultimate decision maker, but unless they're all, some of the open source ones may not. But what would you like to see? PHP, of course, has the voting with the RFCs. How do you feel that's working for the PHP project? And would you recommend any other direction?
So I've gotten involved in PHP internals over the last year or so. I've proposed a few RFCs. Actually, just this week had enumerations pass for 8.1. So PHP 8.1 is going to have enumerations. Yes! To be perfectly honest, I'm in absolute shock that PHP runs as well as it does, given how disorganized it is. It didn't used to. The RFC process was introduced in 2009 as a way to provide some kind of structure and some kind of order to the system. And it was enormously helpful, both from a quality of code perspective and a consistency of features, and also just people not hating each other. So having that formality and having that process made things better. I would love to see the project adopt a more general vision of what kind of things are and are not good to try and pursue, how they should be done. Last summer, I actually proposed an RFC along with Mark Randall to plan ahead for how we're going to use namespaces for internal code. And it got shot down. It did not pass, which is unfortunate because we are now arguing on every other RFC for this cycle. Should we put this function in a namespace? Which namespace? Should we be using namespaces at all? And the fact that we have this argument individually on every single RFC because there wasn't an upfront plan and agreement for how to use namespaces is a process failure. It's a lack of leadership problem. PHP is never going to have a BDFL the way a lot of projects do, but it'd be really nice to have some kind of agreement on these are the rules we're going to follow that we can agree to before we start actually running into problems with them. I would love to see something like that around a number of things. But that is, PHP is a mess, but it works despite that, much to my continual shock. I spent 10 years working on the Drupal project as one of the leads there, which despite technically having a BDFL was also a leaderless project. And that's why Drupal is a complete mess. And it took 5 years to clean it up of just people stepping on each other to clean that up with Drupal 8 to flush out the complete and terrible inconsistency that was Drupal 7. And it wasn't even successful. So yeah, a leaderless project can go very bad very deeply.
Good points. Thank you.
Another question. What problem is PHP 8 solving over 7.x?
That's an interesting question. And the fact that there is no single answer to that is kind of the point. PHP versions don't really have a planned, this version is all about X or Y. They have, this is the stuff that people happen to work on in the past year, and we're now going to tag it. In the case of 8 in particular, what emerged organically was mostly, I would argue, about simplifying things, making complex tasks or verbose tasks simpler and easier to do. But that's me projecting backwards onto it, not anything that was planned specifically by anybody. And if you look at all of the changes in PHP 8.0, they're kind of all over the place. There's some things that make code just easier to write, like constructor promotion. There are some things that introduce completely new features. There are things that are make common patterns easier to implement. And it's just really a grab bag of stuff. I think it's a very good grab bag of stuff. I'm really happy with PHP 8, but it was not planned, it was emerged.
If I could, I'd just like to take exception to one thing you said about caching.
Okay.
A couple years ago, we created some Alexa skills in PHP, and we put them on WP Engine. I think they're out of Chicago, and they had a caching solution that made PHP run fast enough to run Alexa skills. You were talking about, either it fits the framework or it doesn't. I don't know that it was proprietary, but it was a different approach than some other shops had taken. You want to comment on that or not really?
So I can't speak to what WP Engine does in particular. I haven't worked with them. However, I will bet money that what they're doing is just a very aggressive implementation of HTTP cache spec. They're not doing anything that is violating HTTP. They're just using the HTTP cache protocols very, very efficiently. Because if they were trying
fair
to
enough. I can't speak to it either. I don't go that far under the hood anymore. But interesting. I will look into it though, and maybe follow up with you.
Now, I have done some work with caching, and I have looked into a number of things there. And HTTP caching is a complex field, and doing it right is not always trivial, and can vary depending on the complexity and type of application you're building. Something is like, as an example, if you're doing something that is all static at runtime, you don't need per user variation. Pre-generate everything, push it to a CDN, and forget about it is super fast and super effective. In part because then the CDN can do all of the caching geolocated close to the users. If you have an Alexa skill, then depending on the skill, some skills don't need to be user sensitive. They're like, what's the weather outside right now? All it needs to know is the zip code you're in. And so, you send an HTTP request with a zip code in it, that's super cacheable. You can cache that for an hour, and then one person from a zip code makes that request that hits the backend. It then gets cached for an hour at the CDN level and never touches PHP again. Great. Order something on my Amazon wish list. That needs to go talk to the server for every request to look up that user's information and so on. So, however, something like that, you could also not have a single backend server. You can have that logic pushed out to 50 webheads all spread around the world, all of them behind a separate CDN instance. So, in that case, you're not caching, but you are taking advantage of geolocation and the fact that it's a stateless application. So there's a lot of complexity that goes into that sort of thing. But if you want the browser to understand what you're doing, you have to follow specs.
Thank you.
Thank you, Larry. Excellent presentation. I appreciate your time, and so a big thank you to Larry for his time and the help there. We'll move on to the prizes and stuff. And then if anybody wants to hang on afterwards and chat, that's fine too. Larry, if you go ahead and end your presentation, I'll share my screen again. First, we are looking for more speakers for the coming months. I do have 4 more Sunshine PHP Elephants to give away. Larry will be getting one in the mail here next week. He's a lucky recipient of that. as did our speaker last month. So if you are interested in getting a Sunshine PHP Elephant, they are highly valued. They're amazing. They're awesome. They're soft and cuddly. Talk to myself or Derek afterwards, and we can we'll get that set up so we can have some speakers, show some content, and get you an elephant.